Okay, I'll start. Hello, everyone. Welcome to the IAP lecture on TTS, short for text-to-speech today. It's my pleasure to be the speaker. So let's orient ourselves. Where are we? Recall from lecture one this diagram where when somebody is talking to Grace, you would say something through your vocal cord and pass sound waves through ASL, and then Grace thinks about what to say in the dialogue system, synthesize the voice, and then relay the voice back to you through the phone. And today, this is where we are. We are talking about the speech synthesis part. So TTS is short for text-to-speech. So this Monday, you heard Wong Kim tell you about ASR, automatic speech recognition, that transforms sound wave vibrations in the air into a string, a text, hello. So TTS is like the reverse process. It goes from this text here, hello, and it tries to produce a sound wave that sounds like hello. So unlike ASR, it is going from a more simplified object into a more complicated high-dimensional object. So it's a generative model in that sense. And TTS has a really, really long history. So I would begin with an example. In the 1769, this guy, Wolfgang von Kampelen, he built a speaking machine, which is essentially a mechanical model of the human vocal cord. I heard that he spent 20 years of his life working on this. So this is how it sounds like. So as you could see, to operate this machine, you actually have to mechanically press the air inside and then control the air opening. But it sounds vaguely like a human voice. So fast forward to 20th century, we now have electronics. So people built an electronic version of the human vocal cord, and it's called a voder. So in this case, the left hand of the operator will control which vowels to make, and then the right hand will control which consonants to make. And it sounds like this.
Say she saw me with no expression.
She saw me.
Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
So controlling such a device is actually need a skillful operator. It's like playing a piano. It's not so easy to say, just give it a word and then ask it to pronounce it.
Say she saw me.
So about 20-something years later, IBM made the machine 1794. It was made by actually a physicist, John Kelly, with his colleague, Louis Gerstmann, and it weighs 100 pounds. But here is how it sounds like.
Daisy, Daisy, give me your answer too. I'm half crazy, all for the love of you.
So it sounds reasonable now. It could just accept text as a pure input and then output the waveform. But the problem is it's huge. And then several years later, one decade later, in the 1980s, they made a miniaturized version, and it's called a deck talk. In this case, it could fit in a small wheelchair. So here is how it sounds like.
The fact that you are listening to me now shows what technology can do, even if it does give me a Scandinavian or American accent.
So people can now use it as a mobile device to generate a voice. which is nice.
The fact
And then let's fast forward, jump to these few years. With the explosion of work in machine learning, deep neural networks, people are now using neural network in general to generate the speech. And the state-of-the-art model, as far as I know, is a model called natural speech. And it would sound really natural, as the name suggests. So for example, for this text, as effectually to rebuke, it sounds like this.
As effectually to rebuke and abash the profane spirit of the more insolent and daring of the criminals.
Another example.
It is not possible to state with scientific certainty that a particular small group of fibers come from a certain piece of clothing.
So this sounds to me almost indistinguishable from just regular human speech. So we have come a long way. So today we are going to introduce you what goes on inside the TTS system and what we could improve upon this TTS. So first, why do we want to have a TTS in the first place? As you could probably see, speech is many people's preferred way to communicate information. And it's the natural way that humans are evolved to communicate with each other with. And the transmission rate for speech is actually quite high. It consists of about 120 to 180 words per minute. And we don't need any special equipment like pen or paper or a MacBook or iPad. So it's really nice to communicate with speech. And other than just words, which can be captured in a text, speech can actually contain more information. Like the tone of your speech can tell other people what kind of emotion you're having. Like for me, probably you guess I'm nervous. And then sarcasm. So the tone variations can convey extra information. Also, there is a personality associated with your voice. You could guess what kind of person just from listening to his voice. So having a TTS output would make the interacting user feel very natural to interact with the computer, and makes it feel more alive and maybe a bit magical. So that's why products like Siri or Alexa or Hey Google, they would rely on TTS to generate the output. So this is an overview of what we are going to go through today. So we are going to give a tour of what happens, how it is made, that given a text input, how does the wave output is generated at the far end. So in the intermediate process, it goes through several stages. There's a front-end component that just processes the text into a number of phonemes, which represents the phonetic units. And then from the phonemes, we have a component that synthesizes the MEL spectrogram. And then thirdly, from this MEL spectrogram, we have a unit that synthesizes the time series signal, the waveform. And there's an extra part component, which is how do we control the output waveform. Oh, no need to be nervous. You don't seem nervous, but hard to shoot. Okay, maybe I need to speak directly to the microphone. So I need to turn around. Okay, thank you, Joe. Okay, so let's start with the front end component. So front end does the following. It would convert text into phonemes. And roughly speaking, it can be divided into two parts. First part is to take in whatever random text you have, which might contain some special symbols like this $sign or abbreviations like ML dot. We need to so-called normalize it so that you have just number of words, which is easier for the downstreams to handle. And then starting from this number of words, we phonemize each word. So take each word and then convert it into this number of phonemes here. Say, hello, Mr. Strawberry, you won $10,000. It would convert this MR into Mr., this $sign symbol into $10,000. And then each word would then be translated into a number of phonemes, even with the comma sign. So we are going to go through each part. So the first part, normalization, is quite straightforward. Mostly is rule-based, using regular expression matching. So for example, if people give you some email address like logman@gmail.com, you would recognize this @sign should be made into English word AT, and then this dot would be DOT. If you're given a number, a long string of number that has multiple commas, you might not want to contain these commas in your final output. So this 7-digit number, it becomes like 1,230,367. Also, $signs you need to convert appropriately. And for years also, say this year, 2021, this is how usually American people pronounce it. So we want to convert it into a nice form for downstream tasks. So once you have this normalized text, the next step would be converting those into phonemes word by word. This step is also called graphing to phoneme. Graphing because this is how the symbol is being written. We convert into phoneme because this is how the word is sounds. So this 10,000, it sounds like T, N, and then sun. So it converts into a string of phonemes, which makes the downstream task easier to digest. For most cases, we just convert word by word using a dictionary lookup. Of course, there are some trendy words which might be out of the dictionary. In that case, we might need to do something clever, like trying to run a simple neural network model, for instance. And this step is nice to have because if the TTS system fails to pronounce certain words, we could try to change the dictionary or maybe try to fine-tune this model so that it gives you the desired pronunciation without retraining the whole downstream part. But this part is actually not so easy. So there's a challenge of so-called homographs, which have the same symbolic form in graphics. So this word, we will pronounce it differently depending on whether we are saying it this way or that way. So we will record this call, or we say, let me look up your record. So depending on this, whether this word record is a verb or a noun, it sounds differently. So sometimes we might need to do some fancy tricks like using a part of speech tagger and assign different phonemes for that. And in some other cases, it's also context dependent. So it's demonstrated from this meme. How do you tell a plumber from a chemist? Ask them to pronounce this word. So a chemist might pronounce this as anionize. A plumber might pronounce this as unionize. So it's really tricky, depends on the context. So that's the end of the first part on the front end. Any questions so far? Okay, yeah, that's quite straightforward. Good to know. Let me know if you have any questions. You are free to interrupt me at any point. So let's go to the next part of spectrogram synthesis. This is actually the meat of the whole TTS modeling. So a case study I'll be going through today would be so-called a Tacotron 2 model. So what it does is it takes a number of tokens, which are phonemes here, and then it outputs the MEL spectrogram at the end. So this complicated diagram shows you that the MEL spectrogram, the phonemes are first passing through some embedding layers, convolution layers, LSTM, this whole encoder component that takes the whole phoneme sequence and encode it into a hidden state in this position here. So everybody can see the mouse pointer, right? Okay, or I could use the state if I can. So phonemes goes here, hidden states goes there. Okay, so this hidden state would then be fed into another giant component, the decoder, that runs autoregressively, meaning that it would try to process the frames, the input. It would try to make the output MEL spectrogram frame by frame. So the MEL spectrogram output at this time would depend on all the MEL spectrogram output at the previous steps. So it takes in the hidden vector, do something, and then outputs MEL spectrogram frame right here, which then get fed into the into the prenet for generating the next Mel spectrogram frame. So in that sense, it is also autoregressive. It's not nice to have an autoregressive model because it makes it really slow. The time it takes to generate a long wave output would then be proportional to the length of the wave. But it has a good mean opinion score. That means it sounds nice. Compared with just human speech, it's not that far away. And it's a relatively small model with 26 million parameters. It's described in this paper, actually published, I think, in 2017. The reason it's called Tacotron is because these authors like tacos. Machine learning people are not the best at naming, but this is what the loss function looks like. It basically has 3 terms, pre-term, post-term. These 2 terms means that you compare the Mel spectrogram output, say at this point, with the ground truth Mel spectrogram, and just cook up some maybe L2 difference. So that's what the pre-loss term means. Post-loss term means that you take the output, feed into another extra postnet, add the output into the original thing. So you get the entire, at the end, a Mel output here. So this is the final output. You compare this output with the ground truth, that gives you this L post. And finally, this L stop term means that, well, the Tacotron needs to know when to stop, when is the wave audio stopping. So it also produces this stop token, which is 0 or 1. 0 meaning it's not time to stop. 1 means it's already time to stop. This has a dimension of number of Mel frames. So for every Mel frame it produces, it knows which point it is to stop. And we use a cross-entropy loss to compare it with the ground truth. So for every ground truth wave, we know when it stops. So this is how the stop token is trained. So this is a basic model that is battle tested, quite nice to use. And I want to bring to your attention that there is also a local sensitive attention part in this Tacotron. So meaning that at every time step where it's trying to produce the Mel output, it will try to attend to the hidden states produced by the phoneme. So it try to attend to a particular phoneme when it's trying to predict a particular Mel frame. So this kind of attention, we could plot it out. So at which time it is attending to what kind of phoneme. And in general, we expect this attention to be trained in a monotonic increasing manner that has a very sharp shape here. So if you see something like this, sharp, nice, monotonic, no breaking, then it usually sounds good. So this is how it sounds like.
My name is Grace. Thank you for calling.
My name is Grace. Thank you for calling. But in the case that if you see the attention seems to break in the middle, this means that it's actually skipping over some phonemes. So you might sound a little bit weird. It's like it's skipping over some part of the test input. Here is what it sounds like.
Thank you for calling Bright Smile Dill.
So you might notice that dental is not very pronounced correctly here. So in this way, this alignment graph can be used for debugging. And usually good alignment, meaning good and sharp, would lead to a good generalization. So this is some comment. You could also use it for making time alignment with the phonemes. But so that's the end of the spectrogram synthesis part, and we'll be moving towards the Mel, the waveform synthesis component for the talk. So we could stop for any questions if there are any. Okay, sounds good. So waveform synthesis means that, so now you are given the Mel spectrogram. You want to construct the time series signal. Essentially, you want an algorithm that reconstructs the time domain signal by filling in the missing phases. Because recall from Wong Kim's lecture, Mel spectrogram, you just take the magnitude of the Fourier transform of your time series signal. So you're getting rid of all the phases. So how do we fill those phases back, given the magnitude? There is an algorithm, quite famous. It's called Griffin-Lim algorithm. It has no parameters, and it works relatively simply. The way you do this is you take your magnitude and then start with some random initial phases, which I call angles, and then do the following. You set your output spectrogram magnitude and angle to be the initial magnitude angles, and then repeatedly do the thing that you do inverse Fourier transform of this spectrogram, so you get a time domain signal that might have a weird phase component, but then you do a Fourier transform of this inverse signal back to a frequency domain signal. After that, you reset the magnitude part of this frequency signal to your given input magnitude. If you repeatedly do that, then you find the result would tend to converge, and this algorithm would know how to fill in the phase signals eventually. So at the end, you take the spectrogram from this loop and then do an inverse Fourier transform to get a time domain signal. The good thing about this is has no parameters. You don't need to train a model for it, but it doesn't really sound really good. So there are some alternatives, of course, you might guess, with neural networks. So a case study we'll be showing is so-called the Hi-Fi GAN, standing for High Fidelity Generative Adversarial Network. So this network has two components. One is a generator that acts to generate a time domain signal, a wave signal from a given MEL spectrogram, and also a discriminator component that takes any time domain signal, try to predict whether it is real or fake. If it's real, then it says 1. If it's fake, it says 0. So when we train the model, we also have many ground truth time domain signals that the discriminator is supposed to suggest it should be real. So to train these two models for the discriminator, we ask it to do the following. Whenever you see the real deal in X meaning something from a real data set, you need to predict 1. So you need to minimize this term here. And if you see something which is generated from the generator, given from the generator output, then you need to say that it is 0. So minimize this term. For the generator, your job is to make the discriminator thinks whatever you generate is legit. So you try to make the discriminator generate 1, minimize this object. So these two models would then train together, and then the discriminator gets better at telling which is good, which is bad. Generator gets better at fooling the discriminator. Eventually, it generates really nice audios. So here is some figure to dive into the actual architecture of those generators and discriminator is not really important. Generator essentially is a smaller model, only has 14 million parameters, and it's also not autoregressive. So it could generate the whole time domain signal at one go. You don't need to generate it time sample by sample, which makes it quite fast. And the discriminators are where most of the parameters live in. It has 71 million parameters, like 5 times the size of the generators. It's distributed between 2 different types, one called multi-period and one called multi-scale. Don't worry about the details. Essentially, they are trying to extract different features of the time series signal by rearranging them in different ways or applying convolution with different window sizes. So that's the discriminators. So that's all for the waveform synthesis part. Now we want to move into the 2020s. So in the recent years, there are more advanced models which no longer trains those 2 models separately. As you might guess from listening to Wong Kim's lecture, the overall trend in machine learning is to make things more end-to-end, combine more models into the same training pipeline so that they could be optimized at the same time instead of optimizing them individually. So that's the theme of what we are going to talk about next, end-to-end TTS. We no longer do this kind of separate model training separately, but rather we want a uniform network to do the synthesis at one go. You might have questioned at this point, maybe we'll also include the front end into the whole model so that it would directly generate waveform from the text. And yes, such model exists and it works, but we'll leave this part untouched because sometimes it's nice to have phonemes for us to manipulate. But we'll focus only on the second end-to-end part. So one famous end-to-end model is so-called a VITS model, published 2 years ago by Kim and other people. So this is a complicated looking diagram. We could just walk through this very roughly. So when we train this model, we need to provide the phonemes, and we need to tell the model how it sounds like in the waveform here. We also take the spectrogram of the waveform and provide it as part of the input. What this tries to do is it has a text encoder component that, again, similar to the encoder part in the tachotron, encodes the phoneme into some hidden vectors. But more than that, it has a decoder component here, which is essentially the generator in the hi-fi GAN, already built into this whole architecture. So the linear spectrogram passes through some encoder, produces Z, which you could think of as something like a MEL spectrogram. Not exactly, but something like a MEL spectrogram. Then it goes through so-called a flow component, which is essentially an invertible neural network, and gets another hidden state. And then there is a monotonic alignment search, meaning that you take the hidden state, produces some Gaussian distribution, Gaussian center, and Gaussian variance. And then you try to make an alignment. So you repeat those frames from the phoneme level into the frame level, such that it maximizes the probability that the FC you see here belongs to the distribution you predicted here. So you do this alignment search to maximize the probability. So during this alignment search, you will be able to know how much MEL frame does each phoneme take. So this is the integer vector D here. Once you extract this D, you could train this stochastic duration predictor. Essentially, this component is trying to predict how many MEL frames should each phoneme take over. So there is a part that tries to train this. The arrow here goes in the other way because this component is reversible. So it's try to take the D here and the hidden vector try to produce noise in a unit Gaussian. When you run the model, it goes in the reverse direction. You take some noise in the unit Gaussian and the hidden state and then produce some numbers which essentially predicts how many MEL frames should each phoneme take over. So comments about this. What makes speech sounds natural is that even for the same person, same text, you ask me to say the same text several times, they might sound slightly different. That's because humans are inherently noisy. For each word, you might pronounce it in slightly different time durations. So this noise here is essentially capturing that noisiness. If you sample a different point in this noise, you might say the same sentence in a slightly different way. So maybe this is part that makes it sounds natural. So the loss function for this VITS has many components. This L is the reconstruction loss, which means that you need to match the waveform you produce at the end with the input waveform. And then you have this KL divergence term, which is some internal loss for making this flow work. Essentially tells you that if you take the linear spectrogram, fit in encoder, you get this C here, you should get the same thing as if you fit the phoneme there and then go the other way. So if you go the other way here, you should get the same kind of C here. So those two distributions should match together. L duration is not loss for training the predictor. You want the noise produced here to be a unique Gaussian. And then adversarial loss for generator is same thing as the hi-fi GAN training. And this feature matching loss is also a part that is used for training the generator. So that's basic idea. Yeah.
The spectrogram that with like during the training versus the input spectrogram, is that like the complex spectrogram then?
It's the magnitude only.
In this kind of thing, what is the phases?
The phases are filled in by this decoder part. So up to this point, everything is just magnitude. This decoder is the same thing as a generator in the hi-fi GAN. So it fills in the phase information. Yeah.
And the loss of that is again just the GAN loss. There's no actual
the loss of this is from these two terms. So these two terms would train the decoder part. So input would, we also have the raw time signal input when we train the model. So that is used for training this this part here. Could you please read? Okay, the question for the virtual audience is that the linear spectrogram here, whether it's a complex spectrogram or just the magnitude. So the answer is it's only the magnitude, and the phase information is given in the raw waveform. So I think it was just unclear whether the raw waveform is provided as part of the training process. Okay. Okay. So so nice thing about this VITS is it has really high mean opinion score. It sounds almost human-like on some data sets. And moreover, we don't need to wait for the attention alignment to actually train. In the case of the tachotron, sometimes it fails to train an alignment, so you don't see a good sharp line. So then the generalization would not be nice. So here we don't need that. We extract the alignment just from the monotonic alignment search. And we don't need to do two training programs separately. So we could train the vocoder, meaning the waveform generator, together with the MEL spectrogram generator. So optimizing them together makes the overall quality better. And also the duration is controllable. That means if you could look back into the architecture during inference, we have a predicted duration for each phoneme here, say 2, 2, 1 for the 3 phonemes. If we want to control it so that maybe the speak slower, then we could manually manipulate this D vector here. Instead of 1, 2, 2, maybe we want it to be 2, 4, 4. Then the model should know we want it to speak slowly and then generate something that sounds slow. In that sense, it's controllable. Finally, is one big improvement over tachotron 2 is now it's not autoregressive. You generate the entire waveform, entire MEL spectrum in one go. So you don't have this linear scaling with the output length. So it makes it very fast. And then fast forward maybe 1 year later, people developed this natural speech, which I gave samples to you earlier. So I would say it's a variation on the VITS architecture, but with multiple improvements here. I'm going to only do a sketching. So one point is that this phoneme encoder, they now have some phoneme pre-training that asks that only trains this part to do the following. It masks out some parts of the phoneme input and try to make it predict the missing phoneme. So it's quite similar to how a BERT is being trained. So the hope is that this phoneme encoder would make a better embedding of every phoneme, knowing its context. And the second improvement is now that there is a differentiable durator that essentially combines the giant part of stochastic prediction, monotonic alignment search. You group all this together into some kind of a differentiable durator. So it could just learn how much duration each phoneme should have. In my understanding, it's sort of like a mini attention model there, but it somehow be able to learn the duration. And then thirdly, in the wave decoder, previously it was just a hi-fi GAN generator. Now it includes some memory to maybe make it more efficient to train. The upshot is that we finally have a TTS model that is able to produce audio that matches the mean opinion score with just a human speaker. So, which is quite nice, able to fool humans now. So that's the part on neural network spectrogram and waveform synthesis. Maybe we could stop briefly here for questions. Okay. Yeah. Yes. So far, this models still use phonemes. Okay. The question is, so far all the end-to-end models they still use the phoneme as the input for the neural networks. Yes, for those that I show you, they all use phonemes, but that is not necessarily true. There are models that use directly the text input. I'll be going through one of them soon. Okay, thanks for the question. So any other question? Yep.
Could you go back to the natural speech slide? Oh yeah, I wanted to ask, is there anything that's really a malframe in here?
Not really a malframe. So you cannot really compare it to a malframe, but I would say that this Q here is sort of like the malframe. So it has a dimension of roughly like a malframe, and if you repeat certain units of Q, it would sound slower in time. So think of this as a malframe, of a hidden state version of a malframe. Not exactly though. Okay, no more questions. Okay, the question was in the natural speech, are there any parts in this model which is like the malframe? Okay. So with that, we could go into the last part of the talk, which is about controlling the TTS output. So why do we want to do that? Inherently, there are many ways to say the same sentence. For a different person, they might say it in different accents, in different speed, in different pitch, in different volume. And in particular, in our dialogue systems, we have many different users for many different situations. We want to pick the right tone to convey the same text, but for different situations. For example, if we talk to old people, no offense, but we probably prefer to speak slower and louder, which is my preference as well. So, and then for example, medical bots or customer service bots, okay, somebody just got into a car crash, somebody is bleeding. You don't want to sound happy, you want to sound sympathetic. Okay, I'm sorry that this is happening to you, and I want to help. This is the kind of information we want to convey. And also for different geographic users, they might prefer different accents. So this is one thing we want to control. So how do we do control? Let me tell you about maybe a more simple case, which is used in so-called fast speech 2 model. So the way this control is, the way it looks like is similar to Tacotron. It has some encoder that takes phonemes, produce some hidden vector, and then it has some decoder that tries to take the hidden vector and produce mouse spectrogram. But what's more about this is that it has in the middle a variance adapter component that takes the hidden output from encoder and then do several things. It would pass through different predictors, duration predictor, pitch predictor, or energy predictor, and add the result back to the hidden vector. In this case, it tells the decoder that there is more information than just the text you are given with. Actually, you need to tell him, okay, the duration, the phoneme sounds maybe slow or fast, the phoneme sounds high-pitched, low-pitched, phoneme sounds loud or soft. Those information you add it back before passing on to the decoder. So each predictor essentially is a bunch of convolution and neural networks. You don't need to worry about the details, but the architecture is looks like such. So when we train this variance adapter, what we do is the following. So usually what we do is just take phoneme and then train encoder, decoder, given the spectrogram, ask the final output to match with the ground truth spectrogram. When we have a variance adapter, then there are more to the story. So this is the extra part. Other than phonemes, we also get some other information like pitch for each phoneme. We assume that prior to starting the training, we already extracted all the pitch information per phoneme. So in this example, I'm trying to predict pitch. So we have pitch ground truths. So what we do, pass the phoneme into the encoder, take the hidden state, get it through a pitch predictor. Pitch predictor predicts that for each phoneme, the pitch should be so and so. So maybe 0.1 for this phoneme, 0.6 for that phoneme, and so on. Once you have this predicted pitch, we would have an additional loss term, L2 loss, that compares between the predicted pitch and the ground truth pitch. So we minimize this in order to train the pitch predictor. After that, we take the pitch, we bin it up, make an embedding vector so that it has the same dimension as the hidden state. Then we add it back to the hidden state vector. You could do concatenation or add it back. The more or less works the same before passing into the decoder. So the key point is that at this point, the decoder should have enough information to know about both what text is being spoken and what pitch was it being spoken, so that it knows that, okay, this spectrogram actually has a high pitch or a low pitch. Now during inference, we don't have all those ground truth pitch. So what we do is take the phonemes, pass through encoder, and it predicts some pitch. So the model knows naturally for each phoneme what kind of pitch it should be in. Then before adding back into the hidden state, pass through decoder. So how do we do control? How do we make something sound higher pitch or lower pitch? Well, we do this. We just manually take the predicted pitch here and really just scale it up, maybe multiply it by 0.5. So they will sound really high pitch, or 0.5, multiplied by just 0.5. So it will sound really low pitch. So this is how we just hand tune the pitch. So that's essentially the idea for controlling pitch, duration, and volume. But there are more control to just this information that you could extract per phoneme. Sometimes maybe you don't want to extract all these pitch ground truths. Then what do? You have many speakers. You want to make the voice. What do you do? That would be the theme for the next part, which is zero-shot speaker adaptation. Yep. Yeah. So the question was, how do you get the pitch ground truth? That is a very good question. So you rely on some libraries that is able to take the input wave, take the input phoneme. First, you need to know which part of wave corresponds to which phoneme. So there is some alignment you need to do. There are some external package that does that. Say Montreal Force Aligner, MFA does that. And then once you know how each phoneme, which time window each phoneme takes in the ground truth audio, you need to calculate the pitch. That has some audio digital processing involved, calculating the pitch. Then you know for this phoneme, you should have that pitch. It's actually a really complicated process. It's the part that I swept under the rug. So thank you for bringing that up. Okay, any more questions at this point? Okay, yeah, no problem, yeah. Yes. I'm assuming actually all this I've only done for one speaker, so I'm only trying to make model for one speaker. The question is for male and female, there are different pitch. So how do I extract the pitch for different speakers? And the answer is I assume there is only one speaker.
But you have
Yes, the question is, I have the waveform where it comes from. I have the waveform where it comes from. Yeah, I do have access to the waveform.
So you don't need to know to set it. Need the waveform to get the.
Yeah, I only need the waveform to take the page. That's right. That's right. But in order not to confuse the model, okay, yeah, what you say is true. Male and female should have different pitch. Okay, thanks. Okay. So, okay, if no more question, then we can move to the next part, which is zero-shot speaker adaptation. So what it attempts to do is the following. You give the TTS some text, and you give it a reference speaker wave. This reference speaker wave could be some random words being spoken. And then you ask the TTS to make the voice of the reference speaker, but replace the text with something else. So in this case, I took a voice recording for myself, and this is how I sound like saying 1, 2, 3, 1. Oh my God, this is really soft. 1, 2, I was saying basically 1, 2, 3, 1, 2, 3, 1, 2, 3. Let me try to. 1, 2, 3, 1, 2, 3, 1, 2, 3. Sorry, I could not make it. Can still hear it fine, thanks. Really, you can hear it.
I think the virtual people will be able to better maybe than
Okay. In that case, okay. So if I ask the TTS to generate this output, thank you for calling Optum. My name is what it sounds like.
Thank you for calling Optum. My name is Grace. How may I help you today?
So it's trying to mimic my voice, but trying to say this sentence. This is how it works, how it's supposed to work. So before training such a model, we actually need to train a speaker encoder model that is a preliminary. So I'll briefly talk about this. This speaker encoder is trained on a data set that has pairs of wave and the speaker ID. And the way it's being trained is that you ask this speaker encoder such that all the waves belonging to the same speaker, you want to map to a vector which is near each other. No matter what this person is saying, you just get to the same vector as close as possible. However, if the speaker encoder see a wave coming from different speakers, say a male voice and a female voice, even if they are saying the exact same phrase, you need to map it to very far away embeddings. So I haven't been clear what means near or far. There are many different ways to do this, but the idea is like a clustering algorithm that try to identify the voice style and group it to the same vector. Different voice styles should map to different vectors. So in this case, you train this speaker encoder, captures only the voice style. Once you have this speaker embedding model, then you could do the following. So I'm be talking about a model called your TTS, which generated the audio outputs you heard earlier. So it's a variation of VITS. So if you just forget about the speaker embedding part, it looks roughly like the VITS I showed you before. Here, the input is pure text. There is no phoneme. You just really just the text, no phoneme conversion. However, in this case, what you do, you take the reference wave, get the speaker embedding, and then fit the speaker embedding into various components of the other model, so that this model, when it's trying to get trained, it also knows what kind of voice style it should try to mimic. So the idea is similar to the variance encoder. You just show the model extra information about the wave that is trying to generate. So this part plays essentially the same role as the variance adapter here previously. Apart from speaker embedding, they also have a language embedding. So it tells which language you should speak in. So you would give it a different accent, maybe. So language ID, maybe if it is Spanish, then even if you input English text, it would have a Spanish accent. But during inference, you can now fit in the reference speaker wave file here to get this embedding. You want the TTS to mimic. So the input during inference would be just the text and the reference wave. Neglect language ID for the moment, and then you would be able to produce a sound wave that mimics the speaker. So that's for your TTS. Yep.
In this, is
Yeah.
the speaker embedding being trained
So
at the
the
rest are separately?
the question is in this whether the speaker embedding is being trained at the same time or separately. I believe it's being trained separately for the reason that training this whole thing needs the input text. So you need the labeled data, also the transcripts. But in order to train the speaker embedding, you need much less than that. You only need what wave and what speaker ID. So you don't need to label all the transcripts. You don't need to put transcript on all the data. So there are more data available to train this part. But I think it is possible to train this together if you have just unlimited data. You just fit it in and then it's an extra loss term there. That works, I suppose. That works. I think it works. So towards the end, I would mention something about ethics. The modern TTS is getting better at fooling humans. So people need to be very careful in using TTS. In the wrong hands, it could do really bad things. If you're trying to do this multi-speaker TTS, you want to ask permission to use a reference speaker's voice, and you need to disclose that your dialogue system is support. So otherwise, bad people may say something like, pretend it to be Lockman and then ask people to send money.
Hello, this is Lockman. Please send $10,000 to me.
Okay, this is not me, so please, no, that is not me. So that's the end of the lecture part, and then I'm going to just ask some questions. Exercise the reader for the next time. So 3 questions. First, how would you normalize the following sentence? Okay. And then second question is, you could visit the Microsoft TTS website. They have a really nice interface. Try to generate the speech audio for this text. The time has come, execute order 66. Try to make it as sinister as possible. And then thirdly, a comparison between TTS and ASL. Just tell me your guess. Compared to training general ASL, do you think a single speaker TTS require more or less data, or whether the TTS model size is larger or smaller? So feel free to play around with TTS and have fun. Okay, so I have a few minutes left. Okay, are there any questions at this point? Is this a Microsoft TTS you're referring to? I think so. Yes, Joe. I think, yes, it's in the Azure website, Cognitive Services. Yes, that is right. Yes, that's the TTS I'm referring to. Any other questions? Okay, so for the remaining time, I'll give it to Wong Kim so that he could present the answers to last lecture. Oh, Joe has another question. Azure Lab is okay. One more question. There is SSML. How would one generate SSML from audio? I don't think you could generate SSML from audio. Rather, it's part of your input. SSML is some markup saying you could encode some part of your text input and say, ask TTS to pronounce it louder or slower. So the way, okay. I don't think SSML is used in training, but only during inference. So say, for example, you want to speak this sentence, but with please send being louder, then your SSML would enclose please send in some language, say open bracket loud, and then open bracket and close bracket loud, something like this. What you do is you then manipulate your, say, in the case of variance adapter, you would manipulate this predicted pitch differently. You will only scale up the pitch associated to the phonemes which are enclosed in SSML. So they are not, SSML is not used during training, but used during inference. I hope that answers the question. Okay, thank you. All right, so the solution. Thank you.
All right. So I'm going to review the exercise that I gave you the last Monday. And the first question is the HMM model in the description in the previous slide. What would be the most probable state when your spouse sent smile, frown, smile face sequentially, and then for this you wanted to calculate the joint probability with your observation and the all possible hidden state, and then keep in mind that when you kind of calculate the probability, you can use the Markov process, Markov chain property, and then also you can use the conditional independence when you calculate the observation probability. So when you calculate the observation probability of the, for example, smile face on the first happy mood, conditioned on the happy mood in the first state, and then you can generally there is a description of from the happy mood to the smile face. There should be probability of 0.9, so you can use that. So multiply all the possible, multiply the observation probability and then state transition probability together, and then you can easily get the joint probability. And then it turns out that the happy mood and the bad mood and happy mood is the most likelihood state. So that's the first one. And then second one, when you have 1 hour of the label speech data, how do you want to train speech recognition? So there will be multiple well, but the best way is the probably want to fine tune from the existing pre-trained model. For example, like wave to back model or whisper or other pre-trained model for different domain, but you can still use their modern E2E encoder capabilities. So then you can fine tune with 1 hour. You can easily get the pretty decent amount of the accuracy. Other strategy you might want to collect more data. There are tons of the data in the internet, so you can crawl but the problem is that there might be some issue that you will easily get the audio data, but you don't get the ground truth of the transcription. So in the case, you can kind of use the machine transcription with your model, and also you can hire some people on label that transcription. And there's a bunch of way. And also, in other ways, you can also train very small model, like HMM, GMM model. It can easily train model with 1 hour speech. You can do some of the job, but you don't expect a good result with that small model. The last question was to make noise robust speech recognition, what can you do with the modern end-to-end speech recognition concept? So I reviewed the spec augment, so you can use that. This is really powerful tool that you can use in training, and also you can use the data augmentation. So what generally people do is you can add noise on your training data, and also you can kind of intentionally kind of distort your training data with some reverberation, reverberation simulation or other you can manipulate the training data. So with that really noise data, you can make speech recognition perform robustly on the noisy situation. Also, some people are working on the noise canceling concept, and then they train the model to cancel the noise from out of the input speech, and then the kind of the filtered and the cleansed waveform can be fed into the speech recognition, and then you can perform the speech recognition. But personally, I prefer the first strategy. Try to train with very noisy data. It can robust more, and but things can change. Yeah, so yeah, this is about it. And if you have question, please feel free to ask me. Otherwise, we can finish here. Thank you.